All right, good afternoon, everybody. Thanks, Energy Simulation, for another year of this great meeting. I just realized that I'm actually squeezed in two upscaling talks, right? Mike and the next one, which is appropriate for what I'm going to talk about, which is model reduction. So let me get started with some motivation examples that we worked on to tell you that we're actually doing model reduction, that is important to do model reduction. The first one here, it is things that we presented in the past few years in this summit, doing conventional reservoirs model reduction, and embedded the reduced model into a optimization framework. And something that you can see here on this right-hand side. And that gave us some savings, not too great savings at that point. But that's something that we kind of looked at a little bit more for the next few years. The next one for conventional reservoirs, so you can see here, it is what we just presented at ATCE. That is basically a 1.2 million cells reservoir that was together with Anadarko, a project with Anadarko. And basically we converted this to a reduced order model that had just to give you a number, and you're going to realize later on when I actually talk about this slide, from 1.2 million cells, we converted something that is in the order of 30, only 30 base functions. And we are able to do optimization on this with a speed up of at least 30x. So it was a nice accomplishment. The next thing that we worked on, it is actually doing model reduction for unconventional reservoirs. And then you can see that we presented here last time. And I'll show some more details on that. Have an unconventional, and we are able to actually do model reduction for flow and geomechanics with savings and speed up at least 50x. Okay? But one thing that you can see from these problems, and even for these 2 days on the summit, we are trying to do something more and push the boundaries, right? And Mike mentioned, we don't even know where this is going to end up, right? So it's the ever-increased complexity of models that we're trying to simulate. And of course, they are getting more complicated. They are getting computationally expensive. So we need to do something else to actually, get a solution I wouldn't say in real time, but sometimes we need a real time, but something that is feasible for the workflow that we are doing. There are several options for complexity reduction, and Mike presented upscaling, and I'll present on model reduction. But also, as you can see in the morning with the Jabalpur, how about data, right? Can we attach data to the to model reduction? And the answer is yes, but we're going to be careful with that. And so the consensus so far is that there is not a single magic bullet that tells you use that particular model reduction algorithm for this particular reservoir problem. So we are trying, in that sense, to adapt all the model reductions to get a robust type of model reduction that is maybe a push button eventually, but it's a hard thing to do. Okay, so let's see if this moves. Yes. So in my research group, what we're trying to do then, we are trying to look at possible ways to reduce computational time. And these possible ways is basically to look at these model reduction frameworks, and that translate into something that is, you want to trade off between complexity and, complexity, physics, and computational time, right? This is by no means a, I didn't mean to say that we start from here, end up in this, but at least from my perspective, this is a physics, coming in a lot of physics, then you do upscaling, you lose a little bit of physics, do model reduction. That, at least from my perspective, it is a minimum loss of physics, and you can even do reduced physics like the capacitance resistivity modeling or other interwell connections type of modeling, and then data-driven that somehow you lose all of the physics, or maybe not, maybe you can retrieve that. And so what we worked on and what we've been working on is exactly this middle range of problems that we still like physics. And to do that, we have been trying to create this, I call this entity here, this reduced order simulator that at least resemble the fine scale simulator. Okay, so and at least you know, this has some meaning as saturation, pressures, permeability, porosity, and so forth. Okay, so what we are trying to do then, so if you look at what we look at in this particular range of model reduction, we have what's called physics-based model reduction. That is basically, you start up with a simulator. You gotta have a, I don't know why this is running, but you start with a simulator right here, and you run this simulator, whatever equations you have right here. So it's a physical-based simulation. So you gotta have at least a simulator that you judge that is a good simulation, and you save up all the state of the system, pressures and saturations. Let me try to go back here one. And once you save that up, pressures and saturations, you create this matrix here that we call a snapshot matrix. And we do some correlation on that matrix, right? And the correlation that we've been using, it is basically to use a singular value decomposition or PCA, principal component analysis, just to look at correlation into this data. And if you find a particular correlation into this data, you can kind of look at how this look like and truncate that data in some fashion, and that basically creates a projection matrix right here, this left-hand side, that you can write the solution pressure saturations as basically a linear combination of those bases. Okay? And why this is physics-based? Because we come back to this equation right here. We come back to that equation, which is your simulator equation, and we simply project that state here with this projection matrix, a linear combination. We project with exactly the same equations. So the methodology seems easy, right? Just simulate, get a singular value decomposition of the states, go back to your simulator and project back, and you are done. And basically, if you look at this equation, it's a much smaller state space-like equation. So you transform something from a millions of state to something that is an order of hundreds, and you are done. Things are not simple, right? So to create that particular projection matrix, that is what is the hardest thing to do, right? And that's what we've been kind of playing with. In particular, we've been playing with trying to find best ways to solve that idea that this is still a snapshot based, which means that you still need to run a simulator. You still need to do to create an input setting that is representative to your simulation. Okay, so basically, let me just go one here. So if you look at this. So in our case, we have these offline computations, which is the basic constructions, and we have the online computation, which is the projection into the equations. And we've been trying to look at ways, if you look at this, if you select points in these grid blocks, we can kind of just pick those points and compute properties at those points, something like that. There is a selection process of those points, okay? And that gives us some ideas from the past 3-4 years that we worked on, POD, POD-DEIM, adaptive POD, and even TPWL, which is a trajectory piecewise linear. Okay? The problem with that, it is when now you try to fix this into a, let's say, well placement problem, that you're trying to design a new well right here, or just place a new well into your reservoir. Things break down, Okay? And the reason is that your basis is based upon that setting and not based upon that setting. Okay? So what we worked on, it is to try to, and of course this is just the nature of the problem, because we are actually inputting things with different boundary conditions, so there's not much that we can do unless to fix that step. And we worked on enhancing this a little bit with adaptations. And what I'm going to show to you that we're going to fix some of this, we even using machine learning algorithms to actually try to find correlations in that new well settings right here. Okay, so just a representative problem that we worked on, just to give you a feeling for. Reduced our model with a conventional reservoir simulation. You can see that basically you get a 30x of speed up. I'm not going to run the numbers here, but we got a 30x speed up with a reasonable response, right? Which is really good. And the question is, can you do better, right? Can we do better? Another example, it is, we try to use exactly the same principle for compositional simulation. And I love to talk with the compositional simulation guys here, because that was really a hard problem that I haven't even thought much about it. And the problem is that to simulate and get the snapshots, you actually need to keep track of the phase changes. Otherwise, your reducer model will not be able to ever capture that change. So we kind of, with a couple of tricks that we used, we were able to simulate this compositional with 8 components and keeping track of those components with an error less than 0.1%. But that gives an increase in computational time. So we are not getting the 30x that we were getting before. So we are actually looking at ways to fix that. So I'll be glad to talk to somebody that can give us a perspective on how to actually keep track of those changes. Okay. Anyway, so another example here, it is that, well, why not to couple this with the geomechanics, right? We know how to do model reduction. And we've done a couple that with geomechanics in the following way. Imagine that you have your flow simulator, you have your geomechanical simulator. Irrespective to the way that you couple both, irrespective, it's coupling agnostic, if you will. I'd like to get a reduced flow and a reduced geomechanical model that can guarantee that the solution it is approximately equal. Okay? So we've done that. We couple that in the same way that we've done with the actual reservoir simulator. And basically, the way it works, you get snapshots of pressure, saturation, and displacement, or whatever other state you'd like to keep. And you create snapshots, you do SVD, and you get the projection matrix, and you project back with proper orthogonal decompositions and other things. And we are able to do that using even trying to do sensitivity analysis on how many fractures you can do. And we are able to get something in the order of 50x as a coupled reservoir and geomechanical model. Again, nice examples that show that model reduction, it is a, you can solve some of these complexity problems, right? Of course, I haven't even got into the detail of the geomechanical, and there were talks here on the complexity of the geomechanical model, and I said, with respect to the geomechanical model, we actually can do that. Okay. All right, so that raises a following question. So you've seen a couple of examples of things that we can do with model reduction. And that is basically, I got to the title of my talk, right? So model reduction at the crossroads. What I mean by that, we attain maybe 50x, a little bit better for some of the examples. But the question is, can we actually reduce this much further? Can you do 100x, a speed up? Can you do 3, 4, 5 orders of magnitude in reduction? Okay. Is it practical? Is it robust? Right? It can just be a push button. And that's we are challenged by one of our sponsors that said, well, that's very nice. You're doing really nice work on model reduction. But from our perspective, we'd like this to be a very simple thing. We'd like this to be a push button. And the user can just, as you do simulation and run, a click on the run, we'd like to click on the run and run your reducer model, right? And the answer so far is that the way that we are doing this, there is a overhead in terms of work, the offline work, that is a little bit more complicated. And so it is not a push button type of thing. Okay, so that's one decisions that we have to make. Should we do some more simple stuff, or should we do more complicated stuff? Okay. Another one, it is, well, I showed to you how to do model reduction at well placement, right? So you can kind of, if model reduction, if the well, you change well locations, your model reduction may break down, so we need to fix that, right? For control optimization, the problem is actually easy, and that's the first example that I showed to you. Right? But can we couple this with other applications? Can we do these production surface facilities? It's another level of complexity, right? Can we do it with seismic interpretation? And the answer is yes, we can do it with seismic interpretation. And I showed to you, I think last year, an example of doing microseismic model reduction. And I'll show a paper on that as well. Okay? So the question is, should we go to simple models or complex type of model reduction? Or should we even use data-driven or physics-based model reduction? Which one is a good one, right? Again, there's not a single bullet, but maybe those questions, it is nice to answer those right now, right? When all these data-driven things are coming up. Okay, so the question is, can we enhance the model reduction with data-driven models, right? Okay, so to answer that, I'll retrieve something from my friend Plato that once said that there is no harm in repeating a good thing, and all learnings it is remembering. And the reason I'm going to do that, because I think that model reduction for flow and geomechanics can be a little bit simplified in some ways, especially for geomechanics. If you recall structural control, right? And if you recall one of my papers 10 years ago, right? We've done some sort of model reduction for structural control. And that traces back from the early findings of finite element. And if you look at most of the finite element codes out there, ANSYS, Nastran, or other things, they all have embedded model reduction algorithms for structures. So why not to use those, like these ones? Dynamic condensation, Guion reduction, substructuring component model synthesis to geomechanical problems. I'm not saying that is easy, but that's at least a little bit more simplified than going through those snapshot-based model reduction. So, just a quick example. So if you have a mass spring damper, you have an equation, you can do projection, exactly the same type of projection that we've done before, and project into this matrix here. And even in quasi-steady, you can simplify things using exactly the same type of projection. And let me show you how the reduce or the projection is actually computed. If you have your stiffness matrix, you can simply partition that stiffness matrix into something that we call a master and a slave, where the slave are the modes that you don't want to have it. So you simply partition this in ways that you find kind of modes that you don't like it and modes that you like it. Of course, this is another issue, but at least coming up with this partition, it is simple. Once you partition that, you can simply create your projection matrices based on doing what's called a shear complement of that matrix K here. And that is your reducer model. Okay? And then one can think about it in the dynamical sense. This is static, but in the dynamic sense, I don't have time to go through. You can use dynamic condensation as well. So far, we are doing this. We tested out in the Mendel's problem type of work, and it works really nice. So here's the displacement from the full model and the displacement of the reducer model that fits really well with the full order model, right? So And we were able to create a reduced model that is at least 10% of the original model. Okay? The idea is now, how can you couple this with flow? And the answer is, I don't know. My student is actually doing that right now. All right, so, but just to finalize my talk, let me just retrieve another finding from, learning is from Plato, right? And this, what we can retrieve from Plato is as follows. SVD, or proper orthogonal decomposition, or PCA, is actually a machine learning algorithm, right? Which was invented 150 years ago. So we are actually coming back to things that we know, things that we learned before. And how this projection-based model reduction is actually a machine learning algorithm. Basically, what I showed to you, you can do the training, we can get the snapshots, we can do identification of the data, can do SVD, or can do something else, can be a machine learning algorithm, and we project that into the smaller subspace. Okay? So projection-based model reduction is actually something that uses kind of a machine learning technique, right? And we can replace the SVD with other machine learning algorithms, in this particular case, with a high-order singular value decomposition. That's the paper that we use for seismic, or even do a neural net, whatever you wanna call that, right? And basically what you're trying to find is correlation into the data. All right, so how have we used that in our favor? For the particular problem of model reduction with a well location problem, we turn into a machine learning problem, and we look at how can we actually fix the basis when we move wells around. And we created a error function based on data input from all these features here, all these features, which turn into a machine learning algorithm, and which basically the projection is actually done with a correction. Okay, and you can see here this toy example. We can actually get a much better simulation or production profile if we use that particular correction. Another example that we looked at machine learning type of algorithm with model reduction, it is this dynamic mode decomposition, which basically you take snapshots right here, and you can, instead of just creating the correlation into the data, you create a dynamical system out of that, which means that you find what is this A here. Okay, so you take snapshots, you find what is this A. Of course, our reservoir simulators is not like that. Our reservoir simulators depend upon a control function, wells. So you gotta have wells. So there is what's called dynamic mode decomposition with controls. Now we have a control function here, wells, and we can do exactly take snapshots of these controls and states and run this DMDC. But again, our reservoir simulator is not like that. We need output functions, things that we are actually measuring. And we have this DMD-IO, input-output, which creates a dynamical system with this ABCD type of system, which is really well studied in dynamical systems type of problems. Okay? So let me just show you, I'm out of time. Let me just show you an example, the example that we looked at, the DMD using embedded into the optimization. This is 1.2 million cells. This is a project with Anadarko, so you can look at the paper. But we look at just doing the DMD, just the DMD, you're able to get, you see the 20 modes right here, from 1.2 million to 20 modes. It's a big, big reduction. And the response is incredible well. But as well, we embedded this into the optimization problem. We embedded this into the optimization problem with a particular trainings here and doing some NPV optimization. And we had a speed up of 30x using this particular DMD model. Okay, so let me just conclude. And I'll skip this for a minute. Let me just conclude this with my conclusions and recommendations. Okay? I think, going just to data science or just data-driven models, it is may have unintended consequences. I'm not saying that it's bad or good, but we don't know what's going to happen if you only use data-driven models. Of course, it's going to help us, but one has to be really caution on the physics, or has to have the physics in mind. I like to call my stuff data physics model, where I incorporate physics into some, and I use machine learning to some extent to help on my physics-based model reduction, not only to replace my physics-based, but to help or enhance my physics-based. And I still like, and I still think that reducer model is supposed to be a projection-based, which means a physics-based. You have a simulator, you have the equations, you project on that particular equations that may guarantee mass conservation, may guarantee all these beautiful things that we know about reservoir simulation. Of course, one can look at simpler approaches, but hopefully next time that I report, we are getting to 100 axes. And I'll be glad to talk to everybody that would like to couple this with other processes, right? That we can try to help on your simulation. Okay, so let me thank you. Open for questions. I'll be glad to answer any questions that you have. Let me thank my sponsors and my students that's currently doing that, and my past students as well. Thank you so much.
Questions? If not, we'll,
Yeah,
Dr. Quick.
So I'm not really sure I want to stand up and give my presentation now, but
You do.
when you say geomechanics, that was all elasticity, right?
That was, yes.
Okay.
Yes.
Yeah, thanks.
Yeah.
That's not really geomechanics, but that's okay.
Right. Well, so we are just finish up a paper with plasticity as well that I can show to you. Yeah.
But then you can critique my art stuff, I'll show you.
There you go.
Okay, thanks for introducing yourself, Dr. Rick Chalatenik.